Okay. Uh, Damanva was removed from the meeting. I don't know why, but any of you can tell Damanva to try to rejoin. Okay, it's removed due to some error. Okay, you can tell Damanva to try to rejoin. Okay, so
Okay, sir.
recording has started. Anything you want to say? Okay, so design of compression members. Let's begin. Design of compression members means basically we will be designing members which is none other than columns. Columns are the members which will take what? Compression. So design of compression members, design of steel structures compression members actually means in a broader sense design of columns. Okay, so basically it means design of columns. So for design of columns, as I have already told you, like we will take one problem, and as we start solving the problem, we will be learning about the theories parallelly. So if you have your IS codes with you, please take out your IS code. Okay, please take out your IS code and you mark a few pages which will be required. Take out your IS code and mark the few pages which I will be telling you right now. It is uh, page number 40, 41, 42, and 43. Okay, 40, 41, 42, and 43. We also need page number 45, page number 44. Okay, so for design of compression members, we basically we will be moving around pages 40 to 45 for design of compression members. Okay, so please mark the pages. We need these pages. Okay, now uh, you see there is a uh, like in page number 44. If you open page number 44, please type Y if you have opened these pages in your IS code. I want this to be an interactive session. Okay, please mark those pages. Whoever is having their IS code at hand, please type Y. Okay, good. Now also you need to have your steel table. So if you do not have your steel table with you, please take it. Okay, right now. Okay, if you have kept it somewhere, please bring it. Okay, please keep your steel table at hand also. So buckling class, you see, there is one point which you need to understand before going to the analysis, which is called as buckling class. Buckling class. Buckling class means basically like, see, there is suppose one column here. Suppose there is one column. Okay. And there is another column. Two different types of columns. Okay. One is suppose, no need to write this down. I am just trying to uh, give you an understanding. But no need to write this part. Okay. Just try to understand the concept of buckling class. Okay. So column A and column B, suppose two different types of columns, different. So if I give a load P to column A, and if I also give a load P to column B, then will they bend in the same manner? What do you think? Do you think they might bend in the same way if the column A and B are different? Type Y or N, yes or no? If we give a load P on both the columns, will they bend in the same way if the columns are different? Do you think they will bend in the same way? No, because they will not bend in the same way. And when columns bend, generally bending is termed as buckling. Generally bending is termed as buckling. Okay, bending is generally termed as buckling. So when we give a load P to column A and same load P to column B, but the columns are different, then the buckling will also be different. Okay, column A will bend in a different way, column B will bend in a different way. So, how to determine in which way they will bend? For that, the columns are basically classified into some groups. Okay, and the groups are actually called as buckling class. Okay, so groups are generally divided into buckling class A, B, C, D. That means if column A and column B are falling in A, both A type, then they will buckle or like they will bend in the same. But if column A is falling in category A, column B is falling in category C, then they will not bend in the same way or they will not buckle in the same way. So there are four types of classes A, B, C, D. Okay, buckling class A, B, C, D. You can see the A, B, C, D are written in the last column of page 44. You can see buckling class A, B, C, D. Have you seen buckling class A, B, C, D in page 44? The last column, the like extreme right, buckling class A, B, C, D. Can you see? So that's the thing. So columns are divided into groups. Okay, so the takeaway from here is that columns are divided into groups. Groups A, B, C, and D. Groups are generally called as buckling class. So there are some ways in which we can determine whether one column is falling in A or falling in B or falling in C or falling in D. Okay, there are some calculations we can do. And those calculations are shown in the second column. Okay, the calculations are shown in the second column. You can see here to determine whether the column is falling in which section or like which section. Okay, so that we will be like discussing when we take a problem. Okay, because discussing with a problem is much better according to my point of view. Okay, instead of going into all theory, if we take a problem and discuss all these things, then it will be much better. Now, let us take one problem. Okay, let us take one problem. You can write down. Uh, and one more thing, in page number 45, in page number 45, these are generally the effective lengths. Okay, effective lengths of columns. And effective lengths we have already got in like in strength of materials, isn't it? Did you get it? Do you remember getting it in strength of materials? Yes or no? Page number 45. Strength of materials, effective length of columns. Do you remember getting it? Effective length of columns. No one is responding. Like, do you remember? Or like, if you don't remember, then I can explain it. Do you want me to explain it again?
Yes, sir.
Yes,
Okay,
sir.
okay. So basically, effective length means, you see, uh, you go to page number 45. You see, suppose, like, let me tell you the first one. Okay, first one, if I give, like, if I explain, then obviously you will be able to understand all the other um, cases. Okay, there are 6 cases. So let me go with the first one. So in first one, you can see there is a column like this one. There is a column. Okay, the column is of length, suppose L. The column is suppose length L. Now what is seen here, that one end is fixed and other end is free. So this column will have a strength which will be equal to a same column which will be hinged on both ends but of length 2L. The effective length you can see here is 2L, right? Effective length is 2L for this column. Okay, this one end free, one end fixed column. The effective length is 2L, and this 2L actually means that this column is having a strength which is equal to the strength of a column which is of length 2L and both ends hinged. Did you get my point? Yes or no? If you have not understood, you can tell me. Okay, I will not hesitate to like explain it once again. Okay, so I will repeat. You see, suppose this is a column fixed, one end fixed and one end free. Okay, one end fixed and one end free, this one. So this column is of length L. If we extend the this same column in a manner, like if we increase the length of this column to 2L and make both ends hinged, then the strength of this column will be equal to the strength of this column. That's like, let me tell you another example. Let me tell you another example. Last one, if you see, last one. This column is, last one is both ends fixed. Both ends fixed. So the column will generally bend in this way. Okay. Now let us forget about the bending. If this column is of length L and effective length is said to be 0.65 L. it means this column will have a same strength which will be equal to, if the column was made both ends hinged, if the same column was made both ends hinged and length was 0.65 L. Same column, this column on the left side, if we make it both ends hinged, same column, if we make it both ends hinged and reduce the length to 0.65 L, their strength will be same. Just like the first one, the column on the left, if the same column, if we increase the length to 2L and make both ends hinged, then the strength will be same. Okay, that's why, like if we see the third one, where the columns are already both ends hinged, the third one, columns are already both ends hinged of length L, then there is no such modification, already both ends hinged. So that's why its effective length will also be L only. This already both ends hinged, and ultimately no modification is required. Okay. In other words, if the column on the left here, if we make this column on the left both ends hinged, then we increase the length to 2L, then the strength becomes same. Okay. Again, in this column, if we make it both ends hinged, okay, if we make this column both ends hinged, then we have to reduce it to 0.65 L, then we get the strength as same. Now, for the third one, this is already both ends hinged, so no need to make any modification. The effective length is also same. Now, how many of you have understood it? Type Y or N, no problem if you have not understood. That means the column, okay, I am glad that many of you have understood it. Okay. If not, you can again go through the recorded video. I am already recording it anyway. I'll be uploading it in YouTube just after this class. One last time I am just saying, just last time I'm saying, if this column on the left, if this column on the left, you have to make both ends hinged, then you have to increase it to 2L. Then we get the strength as same. Okay. If this column on the left, you have to make it both ends hinged, then you have to reduce it to 0.65 L, then you get strength as same. And here the column is both ends hinged, so already both ends hinged, so no need to do any modification. Okay, now you see the second one, the fourth one in page number 45, the second one and fourth one. Second one, okay, second one is a, like you can see one end is sliding. One end is, you can see here, it's looking like this. Okay, and another end is like this. So this part is actually a sliding support. This is sliding. Okay, this is sliding. In number 4 also it is sliding. Okay. So let us take a problem now. Where do we need this? Where do we need this effective length? We need it like because we will in problems, in numericals, they will tell you that, like in the problem that you will be doing numericals, they will tell you that see, this column is one end fixed, one end hinged, or this column is both ends fixed, or this column is one end fixed, another end free. In the problem it will tell you, and correspondingly you have to take the effective length. Okay, and with the effective length you have to do the problem. Okay, so that's why effective length is required, and you don't have to worry about memorizing it. The IS code is allowed in the exam, so no need to memorize it. Okay, but in competitive examinations, obviously for that you have to memorize. You will not be allowed to bring the IS code to the competitive exam. So for college semester exams, no worries, IS code is there. But for competitive examinations, please memorize it. One question is common from this page 45 almost every time in competitive examinations. One question is always common, and the most common is the fourth one and the last one. Okay, the fourth and the last one of page 45 is the most common. You can like mark it. Okay, but not with a pen. You can mark with a pencil. So let us proceed. Now let us take a problem. So the problem is like the column is of 3.25 meter. Suppose column length is of 3.25 meter. Then load is given 500 kilonewton. And it is said that the column is comprising of two unequal angles. Okay, I will show it to you anyway, don't worry. Two unequal angles. The column comprises of two unequal angles. Now, for the material of the column, their Fy value is given 250 Newton per mm square. So, what do you mean by this? You understood. This also you understand, and Fy also we understand. Two unequal angles. What does it mean? It means that the column, if we look from the top, if we look at the column from the top, it will look like this. Are you getting my point? There will be on one plate also connected. Okay, so this is the top view of the column, and these are two unequal angles. That means this leg and this leg are of different lengths. Okay, So what we have to do is we have to design. Design means we have to give the dimensions, like what length we can give here and what length we can give here. That means we actually have to do nothing but we have to select the angle sections that can be placed here. That is called as design. Load is given. So the client is telling you that, sir, the length is 3.25. Load will be falling 500 kilonewton. Material is this one. And we need to make the column with two unequal angles. So, sir, please tell me what angle section can we use. So then it is your design problem. So how can we do it? Okay. Have you understood the question? Type Y. Type Y if you have understood the question. Okay. Then what we have to do is, first of all, we have to assume. We have to start with an assumption. Now let us start with the solution. Okay. We have to start with an assumption that let us assume that the column can carry a stress of, or we can say, let us assume a safe stress. So in columns, we start with an assumption. Okay, so let us assume a safe stress of suppose 100 in 100 Newton per mm square. That means the stress that the column can take is 100 Newton per mm square. Okay, let us assume it that the column can take a stress of 100 Newton per mm square. Now, students might ask, like, sir, from where did you take this range? We might take 50 also, we might take 200 also. Instead of 100, you might take 50, you might take 250, you might take 300. Okay, why are you taking just 100? So in that case, I can just say that there is no such rule, and it is not written in any book that you have to take 100 only. Okay, it is not mandatory, it is not written in any book that you take 100, but in problems, when you see, in most of the problems, they take it within this range. And from where have people decided to take values within this range, 100 or sometimes 90, or but around 100. Okay, sometimes people might take 80, 90, 100, 110. Okay, but it's generally within this range. Okay, so from where have people arrived at this conclusion of taking values within this range for assumption? I can just say one answer, just one word answer I can say, which is called as experience. Because like people who have been doing designs a lot, suppose maybe in the field, or people who have been writing books or doing research, after doing lots of problems, lots of numericals, lots of case studies, it has been like this opinion has formed that like we can take a safe stress of 100 or like 80 to 110. Okay, this is just coming from experience, from people's experience. Okay, so this is not any clause of any IS code or something like that. Okay, so That is the answer, one word answer, experience. Okay, from people after doing so many problems, so many case studies, and they have seen that their solution is obtained when we take generally people are becoming successful with their problems and all if the ranges are taken between this. Okay, so it's like a thumb rule, okay, which has been developed out of lots of experience, lots of studies and all. Okay, but no strict formula is there. So have you understood first step? First step, have you understood? Now, second step, we have got the safe stress of 100. Now, so area required will be equal to load divided by safe stress. And this stress is nothing but compressive stress, isn't it? Because we are talking about columns and we are talking about compression members. So this stress is anyway the compressive stress only. Okay, so load is 500 kilonewton. I make it Newton. Safe stress is 100. So area required becomes 5000 mm square. Okay, now area required is this one. Now next step is from this area required, we have to select an angle section. So we have to open the steel table. Open the steel table. So take one steel table. Okay, you can do one thing. Since like we need an area which is greater than 5000 mm square, you can search of some angle. You open your book steel table and see the content for unequal angles, and consider some angle whose area is greater than 2500 mm square. Because then only what will happen if we join it with, if we join two of them, then the area will be greater than 5000, isn't it? So find one angle which area is greater than 2500, and you can please tell me what angle section you have selected over microphone. Please, I will be waiting. Anyone? Take a minute, 1 or 2 minutes. You see the contents for rolled steel unequal angles. You see the content for rolled steel unequal angles. And tell me one section. I'd be glad to like listen to some answers. In the steel table, the areas are uh, mentioned in centimeter square, so you can multiply 100 to get it in mm square. Anyone? Not even one student. That is a little bit disappointing. You open the content for rolled steel unequal angles from steel table. Binvalang, good, very good, very good. You can say we'll go with it. ISA 150 into 115 into 10. Okay, so you can see here this area is how much? 2552 mm square. Very good, Pinvalan. So now that means if we use this two sections of ISA 150, 115, 10, then we will get an area which is more than 5000. Okay, now for this section, as we have decided, we will be we have to take uh, we have to take three values from the steel table. One is the gross area AZ, and another is the radius of gyration. Okay, two values RXX, RYY from the steel table. Please note it down. Please note it down. ISA 150, 115, 10, AZ, RXX, RYY. Gross area, radius of gyration. So gross area is how much? It is already 2552 we are getting. So for the whole 2552 mm squared for one section. So for both sections it will be 5104 mm square for the whole section which is greater than 5000 mm squared is the area required. Okay, now you can see for in the contents of the steel table now, in the contents of the steel table, there is a content, there is a table where we get some values for gross sections, like not for single, but for two angles together when they become one column. Okay, for this as a whole, we also have some tables. Okay, for this as a whole, we also have some tables. So for that, you can see your steel table. Okay, you can see properties of two angles back to back. Okay, page number 34, you can see. In my steel table, it is page number 34 actually. I follow the steel table by Ramamrutham. Okay, I have been following it since my college days, but in your, if your steel table is different, then maybe you will be finding this table at a different page. Okay, so there is one table which is called properties of two angles back to back. Okay, so first of all, when you go through this table, first you will see the equal angles back to back. Then you will get unequal angles back to back if you turn on the pages again and again. If you keep turning on the pages. So if you see your section, and let us assume that we are connecting the longer legs. It is also told in the steel table. Okay, like properties of two angles back to back when longer legs are back to back. That means these legs are the longer legs that are connected. These are the longer legs are connected. So that means what? This is 115. Okay, this is 115 and this is 150. Longer legs are connected back to back. Now, as you get this section, okay, you will get it. Then you will see like there is a spacing. Okay, here the diagram is drawn in this manner. It's fine, no problem. See, there is a spacing that is there. Okay, there is a spacing. So this spacing we have to determine how much spacing we will give between these two angles. Okay, and obviously this spacing we have to connect it to the plate. Okay, then only the angle sections will get connected. So this spacing we have to determine, and it is there. If you see the steel table, properties of two angles back to back, longer legs back to back, ISA 150, 150, 115, 10. You can see in the extreme right, the options of spacings are given. Okay, distance back to back of angles in centimeter, it is given. So options are given like 0, then 6 mm. Okay, I am keeping it in mm. Then 10 mm, 14 mm, 18 mm, 22 mm. Are you being able to see it in the steel table? Type Y. Good, good, very good. So let us take a spacing of 10. So this we will give 10. Okay, so then as we have told that we need radius of gyration, Rxx, Ryy. So Ryy will be dependent upon this spacing. So if we see the Ryy value for spacing of 10 mm for ISA 150, 150, 10, how much is it coming? It is 47.5 mm. Ryy is 47.5 mm. And Rxx is not dependent on the spacing. Rxx, it is also there in the same table. It is 47.4 mm. Okay, so basically we have got the data that we require mainly. This column has two axes, x and y. So about x, the radius of gyration, about this axis, the radius of gyration is this one. About y axis, the radius of gyration is this one. Okay, now next is the slenderness ratio. Slenderness ratio. Slenderness ratio is actually how it is determining how slender the column is. Slender means weak actually. If we compare two columns, one column is like this and another column is like this. Okay, so just by looking we can see that this column is slender, this column is weak. So slenderness ratio basically determines like how weak the column is. If the slenderness ratio is high, then the column is weak. The more slender the column is, the more value we get for slenderness ratio. We can say that the more slender is the column and the more weak is the column. Okay, so that is done. So how do we find? We find it by the formula effective length by minimum radius of gyration. Effective length we already know. It is given in the question. Okay. If it is not, let me just check it once again. Yeah, you make it effective. In the question, it is written as effective length. Effective length. Okay. Effective length is 3.25. So convert it into millimeter. 3.25 into 1000, and minimum is 47.4 R minimum. That means comparing Rxx and Ryy, whichever is the minimum, that is the minimum radius of gyration. This one is the minimum. So if you calculate it, for the the slenderness ratio, you can see the slenderness ratio when you calculate. Let me do it. Three two five zero divided by 47.4, 68.56.
So,
Yes.
so RXX and RYY we wrote from the previous table, na?
Rxx and Ryy you will be writing from the new table, which is for the back-to-back angles. Okay, not from the table of the single angle, from the table of the back-to-back angles. Have you understood?
Yes.
The table containing the back-to-back angles. From there you will get the Rxx and Ryy. So when you divide it, you will get it around 68.5 something. Have you got it? Have you got it?
Yes, sir.
Okay. And RXX and RYY, always remember, don't take it from the table having the single angle. You go to the new table having both angles back to back. Okay, you check the angle that you have selected. Then from there, RYY you will be getting from the spacing that you provide. And RXX is also in the neighborhood. You can see in the nearby table, RXX is also given. Okay, so slenderness ratio we are getting like that, 68.56. Now, I think my time is over. So what we'll do is we will be continuing with this problem in the next class. Okay. So tomorrow also at the same time we will be joining here, and after this class I'll be uploading it in YouTube instantly. Okay. Any doubt you have, you can ask, and if not, we can end this class. Any doubt?
No, sir.
Okay. Thank you. Thank you for your time.
Thank you, sir.
Thank you.